All right, hello everyone and welcome to the fourth lab of the organic chemistry series this semester. And for this lab we're going to be talking about the Diels-Alder reaction. So we're moving on from some of the spectroscopic methods, analytical methods, and we're going to be doing some synthesis. So this reaction we're doing this week, the Diels-Alder, well, what is the Diels-Alder? The Diels-Alder reaction is a reaction that's named after two people. So one of them is Otto Diels, and the other guy is Kurt Alder, so they took their last names. So if you invent a famous reaction in chemistry, they name a reaction after you. And they discovered that if you take a diene and a dienophile and you heat them up, so this is the Greek letter delta, it means heating, and you heat them, they will cyclize into a ring, a cyclohexene. So we're going to explain what a diene and a dienophile are and why they combine into a cyclohexene. This reaction can be categorized as firstly as a cycloaddition. Okay, so a cycloaddition, so you're making a cyclic compound, and it's an addition, so you combine these two, you add them together. So this compound is sometimes referred to as the cycloadduct. Adduct meaning addition product. Okay, and another way to categorize it is called a 4+2 addition. So the numbers here refer to the number of pi electrons that are going to be interacting in this reaction. So you'll notice that the diene has two double bonds, so each double bond has 2 electrons, so 4 pi electrons here, and then 2 pi electrons in the dienophile. So if you combine 4 plus 2, you have a 4+2 addition. So these two come from the dienophile, and then these two come from the diene. Let's briefly touch on the mechanism. So what are the curly arrows that describe how this reaction occurs? So I'm just going to redraw the two components here. So I put the diene in blue, okay, and then I'll put the dienophile in red, okay. And the arrows look something like this. So there's going to be a new bond here. There's going to be a new bond here. And then there's going to be a bond made here, a pi bond here. And it looks like there's a lot going on, so for the sake of being thorough, why don't we number these carbons? So on the diene, why don't we label them 1, 2, 3, and 4, and then on the dienophile, we can label them A and B. Okay, and let's examine what happened between the starting materials and the products, and obviously this results in a formation of a cyclohexene as we described above. So we're going to have a cyclohexene. Okay, so let's draw it here. So I'll color code them so you can see which part of the molecule comes from where. So these two atoms, these two carbons, came from the dienophile, and then these 4 atoms here came from the diene. Okay, and if we sort of look at what bonds were broken and what bonds were formed, we can sort of keep track of what happened. So bonds broken, okay, and then we'll have bonds formed. Bonds formed. Okay. You'll notice here that what happens is in the reactants, 3 pi bonds are being broken. So there are 3 pi bonds that are going to be broken. And we can look at which bonds broke. So there was a bond between 1 and 2. So this one right here, that one broke. This one between 3 and 4, that pi bond broke. And then lastly, the pi bond between A and B also broke. So A, B. Okay. And now we can look at the bonds formed. So the bonds that we formed in our product, well, there's this new one here between 1 and A. So there's a sigma bond, a single bond. Sigma means single, between 1 and A. There's also a new single bond between 4 and B, for being thorough. Okay. And then lastly, there's a pi bond, a new pi bond between 2 and 3. So that's what gives you the double bond in the cyclohexene. So there's now a pi bond between 2 and 3. And we can use this nomenclature, this numbering system, to analyze complex products. Even though it might not look like how you might make it from a diene and a dienophile, you'll see that this nomenclature is quite useful. Let's talk about what the diene and the dienophile do specifically. What characteristics do they need to do? Do they need to have to participate in this reaction? So we're going to use paper. Okay, divide it down the middle. We'll talk about the diene first. Okay, so the diene, as you can see, consists of two double bonds. It's an alkene with two double bonds, hence di meaning two. Okay, but it can't just be any diene for this Diels-Alder reaction to occur. It needs to meet certain requirements. Okay, one of those requirements is that the double bond must be conjugated. Conjugated. What does that mean? So in order for a double bond to be conjugated, they need to be right next to each other. They need to be adjacent. So you'll notice the sp2 carbons, okay, so the double bonded carbons are directly connected in a conjugated system. So this is okay. However, if you have an example like this, so say you have a diene that looks like this is an example that's not okay. This is not a conjugated system, because you'll notice that there is a CH2, a saturated carbon, that separates the two double bonds. So in this case, this diene would not function well in a Diels-Alder reaction. So that's the first requirement. The second requirement is that the diene must be able to adopt the S-cis conformation. So I'm going to take this diene above, and I'm going to draw it like this. Okay? And you may notice that it doesn't look very similar to what we showed on the first page. So if we rotate this bond, you can see that now we form the S-cis conformation. So this conformation is called the S-trans conformation, okay? And then this form is called the S-cis conformation. So S refers to the sigma bond. So here, the double bonds are trans on the sigma bond. They're on opposite sides of this single bond. But here, in the S-cis conformation, the double bonds are on the same side of this single bond. So this conformation needs to be adopted for this reaction to work. An example of a diene that would not function well is something like this. So if we have a molecule, a diene like this, rotation around this single bond would not be possible because it's a cyclic molecule. So there's restricted rotation in this example. Hence, no Diels-Alder, no Diels-Alder reaction will occur. Okay? Whereas the diene is fairly complex, the dienophile is much more simple. The dienophile, the name comes from diene loving, or diene attracted, which makes sense, right? It's the molecule that's attracted to the diene. Oh, and by the way, it's, so here, just a single double bond. That's the diene. One note though, sometimes this dienophile, excuse me, is actually an alkyne. So sometimes it's a triple bond. Okay, and if that occurs when you combine this with the diene, the Diels-Alder product is not going to be a cyclohexene. It's going to be a cyclohexene with an extra double bond. So the product will look a little bit different. So draw that. Now the product, instead of having one double bond there, it's actually going to have two. So now there's a separate double bond. But the mechanism is pretty much the same. So one of these double bonds swings out, forms a new bond here. One pair of these electrons comes down and forms a bond between here. And then this bond here becomes the pi bond. And then we get a dicyclohexene. Okay. Let's talk a little more in detail about the structures of the diene and the dienophile. So once again, we can divide our paper. Oops, let's get a new sheet of paper here. We can divide our paper in half. If we talk about the diene once more, sometimes the diene has, or sometimes these molecules benefit from having certain kinds of groups on them. So we'll write dienophile again. So we're going to be comparing and contrasting them. The diene likes to benefit if there is an electron with a donating group attached to it. Electron donating group, Okay, and these are often abbreviated as EDG. Okay, so what is an electron donating group? So if we redraw our diene here, and we attach an electron donating group, something like OCH3, methoxy, this atom that's connected to the structure here has lone pair electrons which can donate into the pi system. So we can have a resonance structure that looks something like this. and we can see how this is a resonance structure of that one. And you can also see how this makes this structure kind of nucleophilic. So this carbon is now a carbanion and likes to attack. Okay, let's compare that to the dienophile. The dienophile likes to benefit from having an electron withdrawing group. Okay, so this is abbreviated as EWG. Okay, so an example of an electron withdrawing group is, say, any carbonyl compound. So here I'll use a methyl ester. Okay, and similarly, we can draw a resonance structure in which this group will actually pull electrons into its pi system. So now we're going to have something that looks like this. Okay, and then now this carbon is going to have a positive charge. Okay, and if we combine them, you can kind of see how a Diels-Alder reaction mechanism works. So if we take our diene in its resonance form, okay, oops, forgot a charge, there we go, and then we take our dienophile here in its resonance form. Okay, you can kind of see, oops, forgot a charge here on this carbon. You can kind of see where the positives and negatives attract. So this negative charge is attracted to this carbocation here. It's going to attack there. These pi electrons can come back down, and then this will turn into another nucleophile called an enolate, which you'll learn about later in lecture, and this will attack this carbon. Okay, and then these electrons can be returned to the oxygen, and in turn you form a product. So if we redraw here, okay, I'll put the new bonds we formed in red. So these are the new bonds we formed here, the new single bonds. Okay, and then this is the dienophile portion. And then I forgot to add, up here is still the methoxy. Okay, so you can see how these resonance structures contribute to the mechanism of the reaction. Lastly, I just want to touch on identifying withdrawing and donating groups. So for identifying an electron donating group, how do I know if the group is electron donating? A good indicator is that the atom that's attached to the structure, so the atom connected to the double bond, has a lone pair of electrons. So if you have something like this, you see we have lone pairs there. We can also have not just oxygen, perhaps nitrogen, oops, NH, and perhaps R. Okay, and sometimes if you have carbonyl compounds which are attached by the heteroatom, so for example an amide, okay, so there are lone pairs here on the nitrogen. Okay, so these are all donating groups because the atom attached to the double bond has a lone pair. Okay, now conversely, for an electron withdrawing group, the atom that's attached to the double bond will not have a lone pair. Attached to double bond does not have a lone pair, rather it has a partial positive or a positive charge. Okay, an example of a partial positive would be a carbonyl compound, such as the methyl ester we used in the above example. So because of the dipole from this oxygen, that makes this carbonyl carbon slightly electron deficient. So you can see that this partial positive carbon is connected directly to the double bond, making it an electron withdrawing group. An example of a complete positive charge would be something like a nitro compound. So a nitro compound, this nitrogen will be positively charged. Okay, so we have a positively charged atom connected directly to the double bond. Another example might be cyanide, CN. Okay, and you can look up these groups, they're not difficult to find, and you'll notice the trends. These will become important for next week's lab as well when we do a nitration. Okay, so something to keep in mind. So lastly, let's just touch on the exact reaction we're going to be doing in the lab. What's the exact Diels-Alder product we're going to be making? And we're going to be making this compound here. It has a very complex name, there's no common name, but it's made from these two compounds, 9-anthracene methanol and N-methylmalamide. So the 9-anthracene methanol is going to be functioning as our diene. It's a little confusing because there's a lot of double bonds, but if you look here where my pen is pointing, you'll see the two double bonds located here. So we have a double bond here, and we have a double bond here. So this is the diene. The N-methylmalamide is the dienophile. And you can see it's characterized by it only has one double bond, and connected to it are actually two withdrawing groups. So we see these two carbonyls connected directly to this double bond, and that's what makes this reaction occur. By the way, when I mean benefit from having electron donating or electron withdrawing, it speeds up the reaction. It makes the reaction more likely to occur. And the reaction mechanism looks very similar. So this double bond is going to swing out. It's going to attack there. This double bond is going to come back and attack there. And then this double bond will go here. Okay? And if we want to have our nomenclature, we can label the diene 1 through 4. So 1, 2, 3, and 4. And then in our dienophile, we can label them A and B. A and B. Okay? So the bonds we form are between 1 and A and 4 and B. In our product here, we can use that nomenclature to kind of help us see where everything occurs. So if we label A and B here on the malamide, we know that A is connected to carbon 1 and B is connected to carbon 4. And if we just fill in 2 and 3, you can sort of see how this structure comes together, even though it looks very complex. It's drawn in 3D space. Okay? So this is the Diels-Alder we're going to be carrying out in the lab. What's special about this reaction is it's being performed in water, which is kind of unusual in organic chemistry because not a lot of organic compounds are soluble in water. And this reaction exploits, or fulfills rather, some principles of green chemistry, what we call green chemistry. So what is green chemistry? So this is maybe the first time you're hearing of this term, but green chemistry is sometimes characterized as environmentally friendly chemistry. Okay, and this chemistry tends to be less toxic in terms of the solvents it uses and in terms of the reagents that it uses. Okay, and it also makes use of renewable feedstocks. Renewable feedstocks. And you'll notice that water satisfies all of these principles fairly well. Water is an abundant chemical, so it's found in the environment. It's very renewable via the water cycle, and we can purify it very easily through our water systems. And it's not very toxic. You know, we drink water as long as there's not anything toxic dissolved into it, and it's not very hazardous, so it doesn't it's not very corrosive or it's not very toxic. So that's what's great about using water. Another aspect that is interesting and deals in green chemistry is this idea of atom economy. So what is atom economy? Well, if you think about economics, economics is sort of how humans cope with scarcity, right? There's a finite amount of material, and it's our job to use that as efficiently as possible, so that will influence our choices. In terms of atom economy, we're talking about performing a reaction where there are no leftover atoms. So if you look at the Diels-Alder here, you'll notice that if you were to count every single atom in the diene and dienophile, all of those atoms would appear in the product. There would be no excess atoms that are wasted. Let's contrast this to something like a substitution reaction. So if we have a substitution reaction, say ethyl chloride, and then we mix it with sodium hydroxide, say we're doing an SN2 reaction. So this will attack the ethyl chloride, kick off the chlorine, and then we generate ethanol as a product. But we also generate sodium chloride as a byproduct. So these here are wasted atoms, so-called wasted atoms. But in a Diels-Alder reaction, there are no wasted atoms. So it's said to have 100% atom economy. Okay, so with that note, we're going to carry on to the experimental portion, and we'll see how we actually perform this reaction in the lab. See you then. All right, so welcome to the Diels-Alder reaction. We have our apparatus here, our 100 milliliter round bottom flask, which will be our reaction flask. We have 0.16 grams of N-methylmalamide, so that's a white powder. And then we have 0.1 grams of 9-anthracene methanol, which is a yellow powder. So we're going to transfer these to our round bottom, trying to get everything. So there we go. Okay, there's a little bit of residue on the paper, that's okay. And then we'll take our our N-methylmalamide, our white powder. Okay, so we've added our powders to the flask. We have a stir bar for stirring. And now we're going to add 30 milliliters of water. I believe the actual procedure specifies 40 mils, but we found that you get a little better mixing with 30 milliliters. So we're going to try that here. Okay, so we're just going to add the 30 milliliters, and as we noted before, these two compounds are insoluble in water, even though the solvent is water. And that's what the reaction will be taking advantage of, the hydrophobic effect. So we'll place this into our sand bath. Okay, so that's a little hot, so I'll take this cork ring to kind of help me dig this out here. Actually, I think I will take a pipette to kind of dig the sand out to make a little well. Alright, so that should be sufficient. There's good contact between the sand and the flask. Okay, so we'll take our reflux condenser. So this is supplying cool water from the sink. Okay, make sure we have a good seal. Okay, and then we'll clamp it loosely. This doesn't have to be super tight. So it's just to make sure it doesn't tip over. Okay, make sure the outlet is in the sink, and then we'll turn on the water. Alright, that should be good. So now there's cool water entering here and exiting here. And now we're going to turn on the stirring. So this reaction does need some very vigorous stirring to ensure that everything is mixed. So there we go. Okay, and now we're going to heat it to a reflux. So reflux simply means you're heating the solvent up to its boiling point. And obviously you don't want to lose your solvent, right? If you didn't have a condenser, all the solvent would evaporate and you would just have a dry powder, a crust in the flask here. So you condense the vapor back into here. So the pot temperature, or the reaction temperature, is 100 C, because water boils at that temperature. Lastly, what you don't want to do is stopper the condenser. You don't want to do that, because when you do that, you create a risk of pressure building up in this apparatus. So gases or water vapor may build up in a pressure such that the apparatus explodes in a worst case scenario. So you can even see a little bit of pressure. I don't know if you saw it, but the stopper maybe popped up a little bit. Maybe it won't do it again. So there, you may have been able to see it raised there. So do not stopper that, and everything will be safe. It is not a closed system. Never heat a closed system. Okay, and we're going to heat this until it starts boiling, which is the reflux temperature, and then we wait for 1 hour for the reaction to be completed. So I know I just said that normally you never want to heat a closed system, and for the most part that's true, unless you have special glassware made for it. So this is a sealed tube reaction vessel. So this tube is very thick, the glass is very thick, and it's actually meant for performing reactions above the boiling point at atmospheric pressure. So if you can heat a reaction to a high temperature, it will react faster. That's the general rule of thumb. The specific rule of thumb is that for every 10 degrees you increase the temperature, you double the reaction rate. There might be some variance in that, but suffice it to be said, if we can heat it above the boiling point of whatever solvent we're using, then we can conduct reactions at a much higher rate. So water, which normally boils at 100 C, if you seal it and put it under an increased pressure, which is what this apparatus does, you take a special cap and then you seal this, this will increase the boiling point of water to not 100 C, but perhaps 120 to 150 C. And we've actually done this same Diels-Alder reaction in a sealed tube like this, and instead of it taking 1 hour, it takes maybe 10 or 15 minutes. So if you have the glassware, you can in fact heat things under a sealed system. So you might be able to see it's rated, pressure rated, so the maximum pressure this is rated to is 150 psig, the gauge pressure. And you normally, when you do this, you stick it in a bath, and then a sand bath to heat it, and then you would put a blast shield in front of it. So just in case, in the small chance that it explodes, you're safe. So just thought that'd be an interesting side note. Alright, so you'll notice that we've now reached a reflux. So inside the reaction mixture, the water is heated up to its boiling point, and you may see periodically some drops of water coming down from the condenser. And if you look up here, you can see condensation where the water is condensing. So now that the reaction is at high temperature, and it's probably occurring at a higher rate, let's talk a little bit about how water accomplishes this in spite of that. So despite water being a nonpolar solvent, and not being able to dissolve these molecules, water takes advantage of what's called the hydrophobic effect. So the molecules themselves don't dissolve in the water, and they actually run away from the water molecules when it gets near them. But in running away from the water, they're actually forced together. It forces the 9-anthracene methanol and the N-methylmalonide together because of their shared hatred for water. So that's what's known as the hydrophobic effect. So despite being insoluble in the solvent itself forces the reactants to combine in a very small space, and that's what helps this Diels-Alder reaction proceed. Okay, so we've refluxed this reaction for an hour, and now what we're going to do is I've lifted it out of the sand bath so it doesn't heat it. And now we're going to let it cool to room temperature, and then afterwards we're going to place the flask into an ice bath to try to get as much of the product to solidify as possible. Okay, alright, so we've allowed our reaction mixture to cool to room temperature. The flask is just mildly warm. Okay, so now it's safe to be placed into our ice bath. Okay, so we've made a little ice bath here, and we'll cover it with a bit more ice. So we're trying to get as much of the product to solidify as possible, just in case any of it is dissolved in the water. Okay, and then we'll leave it to sit on the ice for about 10 or 15 minutes. Alright, so we've got our Diels-Alder product now, and it has cooled in the ice bath for about 10 minutes. So now what we're going to do is we're going to collect the solid, so I don't know if you can see it, but there's a little bit of an off-white solid there. And we're going to collect the product by filtration, vacuum filtration. Okay. Okay, so we have our solid here on the filter, and what we're going to do is first, before we dry it out, so it's still a little bit wet, but before we do that, I would like to take a sample for our mass spectrometer. So one way of judging purity of an organic compound is to check the mass spec. So we'll take a little bit of these crystals here. Okay, so you don't need very much for mass spec. Mass spec is a very sensitive technique, and we're going to put some in this vial here. Okay, and then to this vial we'll add a solvent, acetonitrile. Okay, and then we'll take this to the mass spectrometer and we'll show you how you can collect a spectra. Okay, but for our product though, we're going to turn the vacuum pump back on and let it dry under vacuum. Okay, so there's our product we collected from the filter. And now we're going to stick this in the vacuum desiccator until it's dry, and then we'll get a mass on it. Alright, so we're in the mass spec room, so we're at the LCMS, the liquid chromatograph mass spectrometer. We have our sample here, so if you remember, we took a little bit of the solid from the filter and we dissolved it in some acetonitrile. And now we're going to place this into the tray here for the arm to sample. So what you'll see is that this arm will grab the vial, and then it'll take the vial to here. Maybe if I take this off, you'll be able to see it. But there's a robot arm here. It picks up the vial, and then it'll take it here where it will use a needle to take some up and then inject it into the mass spec. Right now there's no column on here, so we've effectively disabled the liquid chromatograph portion of it. It's not going to separate very much. All it's going to do is send the sample directly into the mass spec to see if we have any of the product we're looking for. Okay, so we'll turn on the mass spec, and then you can see the arm inject the sample. All right, so we have our mass spec from our compound here, and it looks pretty good. So if you can see, so remember the x-axis is the mass to charge ratio, which because charge is usually 1, this is basically mass. And then here we have intensity, which we're not too concerned about the intensity of the ions. We're more concerned with what the ions are. And as you can see here, if we look at just above 300, we have a peak at basically 320. It's 319.9, but we round that up to 320 basically. Now what's interesting is the product molar mass is 319, not 320. So what accounts for this extra 1 AMU is not carbon-13, it's actually a hydrogen ion. So the way this ionizes is not through electron impact. What it does is, in the mobile phase, there's a little bit of acid, and that acid protonates the substrate. So it's protonating the Diels-Alder product, and it's adding a hydrogen, and that extra hydrogen adds the extra 1 AMU. And that's what gives you the 320. So if you were to look at this, and you look at the M/Z value, this is not the molecular ion, it's actually M plus H, so M plus 1. If you extrapolate backwards, the molar mass of our compound here is 319. And this corresponds with the nitrogen rule too. So the nitrogen rule says if we have an odd mass, we're going to have an odd number of nitrogen in the compound. And indeed, that's the case. The product has 1 nitrogen in it. So 319, even though this is 320. So, okay. That said, if we close and reopen it again, you will notice that there is a little bit of an unknown peak. I'm not sure what this peak is, but it's right here at about 660. So I actually don't know what this peak is. It could be some sort of a dimer or an adduct. So sometimes molecules will partner up in the mass spectrometer and increase the mass. But suffice it to say is that we have our product and it's fairly pure. And we also don't see any of the ion peaks for the starting materials, for the 9-anthracene methanol or the N-methylmalamide. So if there were significant quantities of those, of leftover starting material, we would see them in this region here, but we don't. So I can say that this synthesis has been a pretty good success. Okay, so we have our Diels-Alder product here. It's been drying in the vacuum desiccator. Now we're going to get a mass. Okay, 13.26 grams minus the tare gives us 0.07 grams. So you can use that value to calculate your experimental yield for this reaction, the percent yield.